everybody. I'm Joseph Poon. Recently, me and Vitalik Buterin released a paper called Plasma. Its goal and design is around blockchain scaling. And first, in order to understand what the construction is, we need to understand the motivations. So with blockchains, the fundamental aspect is that everyone does validation of whatever it is you wish to ensure that you have assurance of, right? The idea is that I don't believe the world, I'm going to check for it myself, right? And in order to do that and ensure that everyone around you does that, because you want to ensure that you do that and similarly other people do as well, that requires everybody to sort of run one computer, right? And that means that on-chain scalability has upper bounds. The Ethereum Foundation and the Ethereum community is doing a lot of work on increasing the core capacity, and there's a lot of talk about increasing the core capacity, but ultimately there are limitations in order to really enable the blockchain to become this world computer, in order to allow the blockchain to encompass all worldwide, not only worldwide financial transactions, but the overwhelming majority of computation in general. We need to be able to think more so than on-chain capacity, right? On-chain capacity, is necessarily expensive, and that's a functionality. And the existing gas costs are already fairly high for computation. In Ethereum and in Bitcoin, it's already several dollars just to make a single payment. So if we wanted to minimize computation as a goal, that means that we should minimize the validation of what we're verifying itself to the smallest component, right? If the blockchain is the ground truth, why don't we minimize the amount of truth that we need to verify? But the problem is fundamentally what happens in the event of disagreement of truth, right? If you disagree about truth, one or both parties are likely insane, right? That's sort of saying that, one person, if you disagree about the existence of 1 + 1 = 2, then there's probably a big problem. And on a technical level, this implies that there's state synchronization that's necessary, and you need to enforce current state. And with global data, it's easy, right? The idea is that if everybody knows about some information, then everyone has sufficient information to validate it. With second layer technologies, the primary complexity is around withdrawals. So we're going to put a little bit more focus on the synchronization across multiple blockchains. And like our discussion yesterday between me, Jaquan, Thomas, Greco, and Vitalik, is that there's a stronger narrative of this multiple blockchains perhaps becoming a defining narrative. Like I said earlier, if last year was blockchain technology in the enterprise sense, this year ICOs, perhaps next year the defining technical design and technical research is around this narrative of multiple blockchains. This is sort of like the theme of this presentation. And I really want to emphasize that when you look at multiple blockchains where multiple participants are dealing with different data sets, data availability is the fundamental issue at hand. So, I'm the co-author of the Lightning Network, and I'm going to go over some light intuitions around, the Lightning and what it is and how it's designed. You can look at prior presentations for details around that. But the notion is that you have off-chain activity with on-chain enforcement. The idea is that you and I can write a lot of legal contracts, but ultimately, if we are in dispute, we can go to court, but we don't go to court. Normally, we only do it in the event of dispute. On a technical level, right, how Lightning is designed is around something we call synchronicity. So there's local synchronicity between two participants. That means you and I both know about the current state and the current truth. We will only move forward if we have agreement on that. Otherwise, we go to the blockchain, right? So this is interesting, right? We don't have to worry about the information availability between us two because we won't move forward if we don't have the information available, right? And that constrains the problem space very, very, very small. But let's say we wanted to take Lightning's concepts, the core concepts of off-chain information, on-chain enforcement, right? If we wanted to do that in such a way where you can do complex smart contracts and more importantly, contracts involving many participants executing on global state. So an example of that is a decentralized exchange. So in a decentralized exchange, you have many, many participants with a single point of execution, right? Otherwise, that's an OTC market without that. So if there's a single point of execution, that means you can potentially have thousands or millions of people relying on shared state and shared execution. So multi-party state transition is going to be a defining importance for scalability on the blockchain and scalability in order to deal with liveness, halting, etc. But the data availability problem permeates all of these issues. And this is what you really need to be thinking about. And there's been a lot of early iterations on scalability, and without taking this issue into account, there are serious risks. So Plasma's primary focus is around resolving this concern. It doesn't fully resolve it, but it resolves it sufficiently well where, given the constraints that you face, you can have assurance within the security model that you can do incredibly high-scale computation. We're talking about potentially, millions to billions of transactions per second. We're not talking about just simple state transitions, but we're talking about complex state transitions. And it's composed as a set of smart contracts running on top of an existing platform. So Plasma is targeted initially to run on top of Ethereum, and it can be written today without any changes in Ethereum. Especially after Metropolis, it's especially robust. With sharding, it becomes even more robust, but it can work theoretically today. So today, Ethereum can encompass all of the world's transactions, financial and computational. Not all, but whatever can be map reducible. And the overwhelming majority of financial transactions can be map reducible. And is compatible with sharding, on-chain scaling solutions, and other research of that matter. So the main point is that if you wanted this system to be able to encompass worldwide computation, we're not just talking about financial activity. We're not talking about derivatives, etc. like that. We're talking about potentially moving WeChat, Weixin, on the blockchain, potentially as soon as within next year or 2 years from now. It can potentially be able to encompass not only financial stuff, but also web services, chat services, complex computation, even on maybe a little bit later ML, right? Without any changes to Ethereum today, and be able to process billions of transactions per second. And we're talking about potentially payment and ledger scalability as well. So what is Plasma, right? Plasma is a construction that allows you to write a library, and you use this library using and impose your business logic on there, include your business logic, and upload the smart contract onto the blockchain. And after uploading your contract onto this blockchain, that creates a child blockchain. And there's local computation within this child blockchain. And the consensus rules are enforced using fraud proofs. And that means that if someone tries to create false blocks, that is enforceable on Ethereum. And within each blockchain, there are unique rules. And you can do decentralized applications on scale. So that diagram, let's magnify it. So you could have an individual smart contract that is a decentralized exchange, one that runs a social network, one that does exclusively micropayments. And interestingly, you can run a private blockchain on top of a public blockchain. Now, private blockchains, in my opinion, are largely, without the backing of a public blockchain, is basically like BS role-playing. You're not, you might as well run a database. But if you run a private blockchain on top of a public blockchain, this allows you to have public enforcement. And that's when the rules of the games really change. That's when you have, the cross-understanding across the entire network. So it's similar to, how, the intranet is not that interesting without the internet. So you can rationalize, or understand the public blockchain as sort of the internet, you know, and you know, if you say the intranet is more important than the internet, you get laughed out of the room. I don't understand why you don't get laughed out of the room today in that case, right? So how does this work? The idea is that, you know, periodically, you know, every time you create, so first step is you create a smart contract, and then there's going to be a block that is sort of off-chain, but it's sort of not, because you have a blockchain in and of itself, right? So you have a block that's created there, and then it's Merkleized and then committed onto the root blockchain. So you could have potentially, you know, billions of transactions inside this block, and it's only commits about, you know, 100 to 200 bytes onto Ethereum, and it's enforceable. Right? This is not like, you know, those proof of existence systems, which doesn't have enforcement. This is full enforcement on Ethereum. If you create an incorrect block, you will get penalized if the information is available. So one can see this as a blockchain within a blockchain, which is enforceable by the root blockchain. And here's a bigger picture of it. So, you know, in a block, you submit a small transaction on the root blockchain, small transaction, and, you know, let's look at what happens if you create a bad block, right? Like, let's say someone is generating a block. Let's say this is some social network or some, you know, financial platform that you're running on top of Ethereum that is processing billions of transactions per second. What happens is, if you create a bad block, you are committing the Merkleized hash and signing it onto the root blockchain. As a result, if other people have the data available, that means they have sufficient information within that bad block to prove that that block is bad. And they submit a compact fraud proof onto the root blockchain, such as Ethereum, right? So this is the fraud proof that gets submitted onto the root blockchain. And that bad block, block number 4, gets canceled and rolled back by everyone on the network. And the person that generated that bad block gets penalized. So what happens is, if you try to create malicious blocks and the information is available, then you lose a lot of money, and anyone on the network can enforce this, and the system gets rewarded for reporting this, and the attacker gets heavily penalized. So there's economic incentive against creating bad blocks, and it's obvious to everybody that is verifying the network. And for those observing the root blockchain, such as Ethereum, if you don't care about what's going on in this blockchain, in this plasma blockchain, you don't need to observe it at all, right? If someone else is running some private financial derivatives network, or some private decentralized exchange, or even a public decentralized exchange on top of Ethereum, you don't care, right? It's none of your, if no one's disputing it, and you don't have money there, it's not your problem. However, if you have money, for example, on a decentralized exchange, you probably want to watch it if you have money on there, and so you verify it. If there's anything wrong, you report it, and it gets rolled back. And that's sort of how it's constructed. So the core novelty around Plasma is around the issue of information availability, though. So if the information is not available, the idea is block number 4 is withheld, you do an immediate exit and join another network. However, you do want block availability on the lower levels, right? And as a result, we compose things in a Merkle tree of blockchains themselves. So what happens is, you can potentially have blockchains within blockchains within blockchains. And the Merkleized commitments gets pushed up each level, ultimately up to the root blockchain. So if one level is incorrect, that can be enforced on any higher level. So block space availability concerns are mitigated. Of course, if the block space availability, you know, if the entire chain fails on the top to bottom, then you must report on the root chain, presuming root chain availability. So if there's any type of failure that's extreme, for example, let's say, or localized, let's say what's disclosed in red, you can broadcast to the first tree depth and transition to another blockchain. So, mass exits and things like that are, more feasible under this construction. And this allows you to only watch the blockchain that matters to you, similar to what we were talking about earlier. So that if you have funds in the third tree depth, you only need to watch what's in your parents. So that creates great efficiency for not only this root system itself, but users of within these child chains. They don't need to observe all of the child chains. They only need to watch what matters to themselves. But what's interesting about this is by composing things in hierarchical chains, you can construct computation along a similar model. And hierarchical distributed computation along this hierarchical model has been a well-solved computing problem. Google publicized and invented something called MapReduce, and there's been many, many algorithms to solve things in a MapReduce based on construction. And this allows us to basically take that work, except add on Merkleized proofs as the construction of Plasma, so that as each map process and each reduce process, you are able to enforce and verify each state transition. So this is an example. The canonical example tends to be word count. I think we should have a little bit more fun and let's say an example of, let's say you had a decentralized exchange. Let's say you had funds in the third tree depth. So if you wanted to do a transaction, let's say you wanted to sell ETH and buy some ERC20 token, what you do is you issue an order on the third tree depth. The order gets combined, and that's a reduce function under the MapReduce construction. And you combine the order books of everybody. And as you reduce for each step, you are combining each order book into a single order book. And that's committed in the Merkleized proof. And then the trade execution happens at the first tree depth. The order matches, and the matching of which orders match gets moved back up to the second tree depth, which is the further map function, and it gets split up in different map functions that in a deterministic order, and ultimately you know that your order has crossed and the order has been committed and matched. And you have your token that you sold to someone else, or your ETH that you sold for a token. This is fairly interesting because you can reason that you can build an exchange, if the code exists today, that can process potentially millions to billions of transactions in a decentralized exchange. And this is applicable to many, many different systems, right? This is applicable towards, social networks, for payment systems, for, non-computing, non-financial applications and financial applications. So when it comes to future work, there's more incentive for exits, minimizing block withholding attacks, using some fun cryptography and mechanism design, as well as token incentives and proof of stake design research. Token incentives are an interesting area of research simply because Plasma, in order for its security, relies upon an incentive around data availability and maintaining data availability. It's impossible to resolve data availability inherently, right? You can't prove which party is withholding data on a lower level blockchain, as far as we know. And as a result, you need economic incentives, right? That's ultimately the novelty of the Satoshi's design, is that it takes economic incentives and applies it to computation, and that resolves a lot of what we believed before to be impossible. And I genuinely believe that if you can say that there's a possibility that this technology could be a core component of scalability of blockchains in the future. It's possible that each specific application may have its own token. And if these decentralized systems end up overtaking centralized systems, this could be a core component for basically blockchain taking over the entire world. So when we reason about what is Plasma, Plasma is about hierarchical enforcement. You have this third, second, and first layer depth, perhaps even all the way up to 20th. Right? It's very similar to the real world, how we have local courts. And if the local court doesn't do enforcement, we go up to the appellate court. And if the appellate court doesn't do it, we ultimately go to the root source of power and truth, the Supreme Court. And in this case, the Supreme Court is the root blockchain, such as Ethereum. And this allows, and it's a public system that allows us to enforce, whether it be public chains enforced by tokens or private enterprise blockchains. This allows us to use a system whereby an open system has deterministic enforcement, and that allows us to actually create scalability. And this allows us to create high-volume, low-cost, decentralized applications. We're talking about potentially billions of transactions, which are nearly free. This allows us to potentially, well, not perfectly free. There's some small fee that you may pay for people running the network, but that could be 1/100th or even as low as 1/1,000,000th of a cent in some circumstances. And this ideally shows you all the path forward. I believe that there's going to be many, many other different approaches. You really need a lot of approaches and be thinking about this, because I think blockchain is going to matter a lot to the world in terms of improving sort of the efficiency and bringing about a better world for everybody. And we really, really need to think about how all these different blockchains interoperate. And this is sort of a contribution in order to understand today, how it's possible today for blockchain to be able to not only process all of the world's payments, but much of the world's computation as well. Thank you.